when we're talking about this concept of translating a given integral from one coordinate system into another, I wanted to be sure to show you an example of working with at least one of the, or with each of the important coordinate systems. Okay, so we've seen examples, and there's example problems in the notes about working with the polar coordinate system in 2 dimensions. In this morning's session, we did an example working with the cylindrical coordinate system in 3 dimensions. So I want to show you another 3-dimensional example now, working with the other important system in 3 dimensions, which is the spherical coordinate system. Okay? So this is another volume integral. So we'll state a problem that we're going to work on here, and then I'll remind you what the spherical coordinate system is. We'll have a look at the Jacobian calculation of it, and then look at evaluating the integral. So this problem is to find the mass of a sphere of radius A. So, effectively find the mass of a sphere of any radius, but this sphere is not made out of homogeneous material. The density of the material varies according to where you are in the sphere. So for the density of the sphere of a ball, the density of the material within the sphere is inversely proportional to the square of the radial distance. Okay, i.e., the density D at a point x, y, z within the sphere so we want it to be inversely proportional to the square of the radial distance. So the square of the radial distance is x squared plus y squared plus z squared. It's the square of the distance of a point from the origin. I want it to be inversely proportional, so it's going to be proportional to 1 over that quantity. Also, there's going to be a constant of proportionality there. So it's some constant k over x squared plus y squared plus z squared. Okay, so we can set this up as a 3-dimensional volume integral, meaning an integral over a volume, over a portion of 3-dimensional space. So, or we'll call it m because this is going to be the mass of this sphere. So it's going to be a triple integral over the sphere. And we're going to be integrating the density function, which is k over x squared plus y squared plus z squared, dx, dy, dz. So the general idea there is you work out the mass of a body by summing up all the density contributions from every point within the body. Okay. So summing up here is integrating. Okay. You look at what the density is at all the points in the sphere, you integrate over all those points, integrating the density function, and that gives you the total mass. Okay. In the situation where the body you're taking the volume of has got homogeneous density, constant density, it's the same density throughout the material, so then this density term here wouldn't be a function, it would just be constant. That constant could just move to the outside. And so you'd have the triple integral of the region, dx, dy, dz, and that would just give you the volume of the region. in the same way that integrating dx dy, integrating the constant 1 dx dy gives you the area of the region you're integrating over. Integrating a constant dx gives you the length of the interval you're integrating. So this integral of just the differentials for the Cartesian coordinates, that gives you the general volume of the region you're integrating over. It's the length of the one-dimensional interval you're integrating over, the area of the two-dimensional region, or the volume of the three-dimensional region. Now, why is something inversely proportional to the square of the radial distance? That's not just kind of randomly plucked out of the heavens. Although it is plucked out of the heavens, I mean, that's got quite an important connection to something quite important. What are you reminded of when you see something inversely proportional to the square of the distance? It's very important in all our lives. I'm tempted to jump up and down at this point. Gravity, yeah? Gravity is inversely proportional to the square of the distance. So whatever strength gravity has here now on me here on the surface of the Earth, if I go 100 meters up, or let's say I go 1,000 meters up, so I increase the distance by 1,000, the change in the effect of gravity is going to be proportional to 1 over the square of that distance. So 1 over the square of whatever, 1,000 meters. Okay. So this concept of something being inversely proportional to the square of a distance is extremely important. It kind of underlies everything in some ways. So we need to be able to handle that mathematically and perform integrals with it. But as it's presented there, it's presented in quite a bad way there. So the Cartesian coordinate system isn't well adapted to dealing with spheres and to dealing with radial terms there. Okay. So this integral is bound to look better when I say look better, I mean actually be possible to carry it out and look a lot simpler. It's bound to look better in the spherical coordinate system. Now, I did introduce this to you before when we were doing the chain rule, and we first introduced Jacobians. So I'll just do a quick reminder of it now. So we've got our plain old Cartesian coordinate system, x, y, and z. We've got a point hovering out in space here. And I'll draw the Cartesian stuff in the spherical stuff in green. There's a certain radial distance r there. That radius line makes a certain angle, which we call phi, with the vertical z-axis. The radius projects down onto a projected radius lying on the xy plane, just a vertical shadow of the radius down on the xy plane. And that projected radius makes a certain angle, theta, with the positive direction of the x-axis. Okay? So this point is described in spherical coordinates as the point r theta phi. Okay. The link between x, y, z, Cartesian coordinates, and polar coordinate system, this was described by the transformation equations. So we have functions for x, y, and z giving their values in terms of the polar coordinates, in terms of the spherical coordinates. Z is the most immediate one to get, because here's a triangle formed with the radius, the angle phi. If you imagine that projected line brought over onto the z-axis, you'll have a right angle up there. So you've got a right angle triangle. R is the hypotenuse, phi is the angle. So you can, Z is the other side. So you can easily express Z as R cosine phi. Look at that triangle. Get X and Y. Well, X and Y are the sides of this triangle in the base plane down here.
if you bring this point down here, my theta is kind of in the way there, but this is a right angle triangle here. This side of the triangle is x. This side of it here is y. So you got this right angle triangle in the base with sides x and y, and it's got an angle theta. Now, in order to figure out x and y coming from this triangle, we need to know what the hypotenuse is of this triangle. The hypotenuse is exactly the projected radius. If you look at this small angles, the length of this projected radius is the same as this length up here. This is just this side is just the projected radius elevated up to the same height as the point. And we can express this length in terms of r and phi. Okay, this side of the vertical triangle, it will be r sine phi. So r sine phi is the length of this hypotenuse side here, the hypotenuse of this triangle. So we know the hypotenuse in terms of r and phi, so then we can express x and y. So x will be the hypotenuse r sine phi times cosine of theta, and y will be the hypotenuse r sine phi times sine of theta. Okay, so that's the spherical coordinate system. Those are the transformation equations. Any questions or clarifications you'd like on that? So, you know, there's certainly a non-trivial relationship between Cartesian coordinates and spherical coordinates, something to deal with. But, you know, once we have gone through the bother of translating it to the spherical coordinate system, the integral will look an awful lot better. Okay? We don't necessarily want to go ahead and try and integrate this thing 1 over x squared plus all those with respect to x, y, and z. It'll be quite awkward. And even describing a sphere in terms of x, y, z is awkward as well. You've got square roots of sums of squared for the radius, so that can be awkward as well. Now, in order to do the translation, remember, to do the translation, we need to translate the function, the integrand we're integrating. That'll look quite nice because this function is just going to be k over r squared. So it's already looking simpler when you go to polar coordinates. We'll have dr, d theta, d phi, and then we have that extra term in there, which is the absolute value of the Jacobian determinant. Okay. So the next thing we need is the Jacobian determinant. Now, I think in my tutorial, I might have done this calculation to my tutorial group, I think, a few weeks ago. So they might be seeing it for a second time, but I don't think I did it in the lecture. So I'm going to do it again anyway, basically what I'm saying. But it'd be a good benefit, and, you know, it mightn't be a million miles divorced around some other determinant type problems some of you are facing at the moment. So it'll be a good thing to see. So we need to obtain the Jacobian determinant, which, remember, is the thing we denote like this. It's a 3x3 matrix of partial derivatives. Okay. I'm just going to call it J because I don't want to write out all that again. So it's this 3x3 determinant. Remember, the old variables, the top ones index the rows. The new variables, ones at the bottom, index the columns. So we've got dx dr, dx d theta, dx d phi, dy dr, dy d theta, and dy d phi. dz dr, dz d theta, and dz d phi. Okay, that's the formula for it. So it's got 9 partial derivatives there. These 9 partial derivatives are coming from the transformation equations, differentiating the transformation equations with respect to one of the 3 spherical variables. Okay. So we go ahead and do that. Remember, you're differentiating with respect to one variable, so you treat the others as constants. Dx dr will be sine phi cosine theta. Will be minus r sine phi sine theta. And dx d phi will be r cosine phi cosine theta. Okay, so looking at the x function, differentiating with respect to r, theta, and phi. When you're differentiating with respect to any particular variable, you're treating the others as if they were constants. Okay. That's the first row going across. And the sines and cosines, so take care you get your plus and minus signs correct. dy dr is sine phi sine theta. dy d theta is r sine phi cosine theta. And dy d phi is r cosine phi sine theta. Isn't it? Lastly, the dz. The dz is slightly simpler. Cosine phi is dz dr. dz d theta is I'm not going to speak until someone else does. Zero. Excellent. There ain't no theta. Well done. There isn't a theta there, so it's 0. And dz d phi? Excellent. On the front there, minus r sine phi. Okay, so there's all our 9 partial derivatives. Okay, it's not looking so bad because there's a 0 there. And the elements in that third row don't look that bad. Now here's where the relevance to some other ongoing determinant problems may arise. So this, hopefully, you're interested in. Get something up like, what do I not do now?
All the.
Sorry?
If they expand it. Right?
Yeah, so I don't want to expand it, okay? I'll have to turn the visualizer sideways or something, although that won't change the image, of course. But yeah, so look, it's 3 by 3. I'm going to have 9 separate terms to add together. Each term I'm adding together will be a triple product. Product of something times something times something. It's going to be horrendous, very, very long, loads of sines and cosines all over the place, very hard to see what's going on. Okay? So I hold back on expanding it, and instead I look to employ properties of the determinant. Properties of the determinant are, okay, there's a whole bunch of them. If you see any 2 rows the same or any 2 columns the same, you know it's the determinant is 0. The action to think about that's going to simplify this determinant is if you can suck out factors out of it. If you can extract factors out of the determinant, okay? But you need to know how factors come out of the determinant. If I wasn't looking at the determinant, if I was just looking at the matrix, and I wanted to simplify the matrix by taking out a factor. So effectively, you're taking out a scalar. You're going to have that scalar multiplying the whole matrix. Then you'll be looking for a common factor in all 9 of the entries. If we were just looking at the matrix and not the determinant of the matrix. Just looking at the matrix, you want to take out a common factor out of all 9 entries, cancel it out of all 9 entries, and write it in the front doing a scalar multiplication of the matrix. Okay. Well, when you're looking at a determinant, that is not how you factorize it. When you're looking at a determinant, you factorize it row by row or column by column. So you're looking for a particular row in which you spot a common factor in each of the entries in the row. If you do, you can cancel that factor as long as you know it's non-zero, cancel it out of the entries in that row, and bring it to the outside. Okay? So you factor common factors out of any particular row or equivalent or any particular column. And that will save us time. We'll be doing the factorization work now on the unexpanded thing rather than having to observe the common factors and perform it on the fully expanded 9 terms of long triple products thing. Okay? So any common factors there that we can see in any particular row or any particular column. Anybody? Yeah, go
R cos phi. Is it phi?
R
The third column.
cosine phi. Well, it looks good there and there, but
That would just be tan phi.
well, okay. Yeah, but then we'd have complications of tan. So that's a good suggestion.
Just R then.
Yeah, R, brilliant. So there's an R. Any other common factors of R that you can see anywhere? Second column, what are you saying? Yeah, now don't be too put off by the factor 0 there. Remember, is 0, when you're looking for common factors, so here you can see, okay, clearly the first term is a multiple of R, this is a multiple of R, this is a multiple of R. Remember, 0 is special in this way that 0 is a multiple of anything. 0 is 0 times whatever. So R is a factor here, R is a factor here, R is also a factor here, because 0 is 0 times R. So I can cancel an R out of here. No bother. You can't ever cancel a 0 out of anything because you can't divide by 0. Okay? So yeah, there's a common factor of R here. There's also a common factor of R there.
Not the sine phi as well.
Brilliant. Sine phi. It's R sine phi is a common factor in the middle column. Excellent. So I've spotted there's a 1 R factor here, and there's a factor of R sine phi there. So let's at least pull those out. So I can take out R squared sine phi, and that simplifies it somewhat. Sine phi cosine theta, sine phi sine theta, cosine phi, minus sine theta. So it really simplifies the middle column. Cosine theta, and I've still got a 0 there. And here I've taken out the R, so I've got cosine phi, cosine theta, cosine phi, sine theta, and minus sine phi. Now, I didn't take you up on your cosine suggestion from there. I mean, equally well, you could say take a sine phi out of that one and leave a 1 over tan behind or whatever. If you don't mind, I won't do that because it'll complicate things down the road, because I'll then be introducing a third new function, a tan. At the moment, I've just got sines and cosines, so maybe keep it like that. Well, we've saved, what we've done there is saved ourselves an awful lot of work. We've identified part of the factorization of the whole thing without having to deal with a big, long expression, which humans shouldn't really deal with. We should deal with it on this level. So maybe now we'll go for expansion. And suggestions for a nice way to expand it would be third row, yeah? Yeah, third row or second column, okay? Because those feature the 0, and the coefficients are simple enough, but it's the 0. So I only need to work out 2 cofactors instead of 3, okay? So now we can expand. Let's go along the third row, say. So going along the third row, I'm going to have a cosine phi times this upper 2 by 2 determinant. So that's a minus sine theta, cosine theta, cosine phi, cosine theta, cosine phi, sine theta. So it's this multiplied by that cofactor plus the middle entry here multiplied by that cofactor, but I can just discard it straight away because I'm only going to multiply it by 0, so I don't need it. Then lastly, plus the third entry, so minus sine phi times the upper left 2 by 2 determinant. So sine phi cosine theta, sine phi sine theta, minus sine theta cosine theta. Agreed? Now, I haven't gone for full expansion yet. I've just expanded it down to 2 by 2 cofactors. But now you see, we can see more of this factorization that we might do. Because look, in this second column here, you've got 2 cosine phis. And in this first column here, you've got 2 sine phis. So that's good. multiplying out those, I'm going to take a cosine phi out of that. So it's be cosine squared of phi times, okay, I'm just going to shorten it, sine theta, cosine theta, sine theta. And then I'll have a minus sine squared of phi times a cosine theta, sine theta, minus sine theta, cosine theta. And just write an S and C for sine and cosine just to simplify it a bit. So I've done more factorization work there. Okay, there's no more factorization work to do. I should just go ahead and do it. Saved me because I noticed I wasn't getting the right thing out. So yeah, see, remember I took the, yeah, so that was a minus sine phi, so it should be sine, minus sine. Okay, now, so now I need to evaluate those, but what do they both come to? The minus 1 that comes to, and plus 1 that comes to, okay? Because it's minus sine squared minus cosine squared, it's minus 1. And it's cosine squared minus sine squared. So cosine squared plus sine squared, so that's plus 1. So you have a minus 1 and a plus 1, but helpfully it's minus 1, but this becomes a minus 1 as well with that one. So it's minus 1 times cosine squared plus sine squared, so the whole thing is minus 1. Yeah. So the Jacobian there is minus r squared sine phi. Okay? So you see the power of using that factorization property of determinants. It saves you having to expand out a 3 by 3 thing, which you don't really want to do. And it's easier to do the factorization at this stage than it is to do it on the expanded one. Okay. Any questions about that? Okay. So this should all whenever you're faced with awkward-looking determinants, the first thing to come to mind is properties of the determinant. Those are the things to think about. Okay? And they can often help you out. Okay. Okay, so remember we have this integral to transform. This mass integral. This thing integrating over the sphere, the density function, dx, dy, dz. So we can now go ahead and do this. So we can transform the integral. So the mass of our sphere is the triple integral over the sphere. I'll worry about the limits of integration in a moment. The density function is k over r squared. The absolute value of the Jacobian is the absolute value of minus r squared sine phi. And then I've got dr, d theta, d phi. Now, I've still got to don't be tempted to say, oh, the absolute value signs cancel out that minus sign. What's the problem with saying that? What's the problem if I say, oh, look, I've got absolute values of a minus quantity. I can just get rid of all of that and just think of it as r squared sine phi. Sine phi, I don't know about. Sine phi could be positive or negative. Sine goes positive some of the time, negative some of the time. So it's not so simple that we can just decide what to do about the absolute value there. So we'll hold off on that. But I can cancel. Yeah, so the r squared is completely The r squareds completely go. The r squareds cancel. So I'm just integrating the absolute value of minus sine phi. Well, I can drop this minus sign. I'm taking the absolute value of negative sine of phi. Well, that's going to be the same as the absolute value of sine phi. I don't want to just, I can't write it as sine phi, but I can get rid of the minus sign. And okay, so it's just the integral of the absolute value of sine phi, dr d theta d phi. Now I've got to worry about these limits of integration. Sorry, the k. Where's k? Here it is. Okay, k is the constant, the constant of proportionality there. I could have written it down here, but I'll just shoot it out to there because it's a constant. It's not depending on r theta. Okay. Now I'll worry about the limits of integration. Let's get our diagram of the spherical coordinates back. That diagram there. Now what's the region? The region is a sphere of radius a. And when you're faced with these integrals, remember I always suggest work from the outside in. So yeah, so phi is the first thing to look at. Phi is the first integral. So between what limits of phi do we want to integrate in order to cover the sphere? Now you got a choice. Okay, normally maybe you think, well, phi is an angle, so you got to go 2 pi to go all the way around. But theta is also an angle. You have to go 2 pi to go all the way around. But you have to think about the combination of the two. We don't have to go all the way around with both angles in order to cover the sphere. What we could do is with the angle phi, we could just go from a 0 angle, so that'll be when the radius is pointing straight up the z-axis, all the way around to just an angle of pi radians, where the radius will be pointing straight vertically downwards. Okay, so it's just my arm going from there, angle 0, all the way down to angle pi. I could just do that for the phi, and that will get me kind of one side of the sphere, like this, and then I could just angle theta go all the way around. And then as my arm is going up and down, and I spin around, my finger point is tracing out a sphere. You know those things in nightclubs or discos, you'd have a bright LED there in the dark, and if I spin around really, really fast, I move my arm like that, what you see is some kind of sphere, like the bright point tracing out a sphere. So the phi angle will only send from 0 to pi. I could have sent phi all the way around and instead just do theta on a half turn. But I noticed that the phi is the angle that I'm taking sine of. And we had this issue, we had to be sensitive to when sine of phi was positive or negative. But this is simpler because on between the range 0 to pi is always positive. So this sine term won't be changing sign over this range. So it's simpler to deal with. Then I can just drop the absolute values. They won't complicate it. Whereas if I was going from 0 to 2 pi, half of the time sine of phi would be positive, and then from pi onwards to 2 pi it would become negative again. So there'd be no single way to deal with the absolute value sign. So I've made the decision to just go from 0 to pi with phi. Then I look at theta. Okay, theta I'll have to spin all the way around. So theta angle was me spinning around here. And the radius, sphere of radius A. So we want to integrate from the center of the sphere out until we reach the point in the boundary of the sphere, which is that radial distance A. Okay. Everybody okay with that? So figuring out those limits of integration, it's not just a one-step thing where you think, oh, sphere, oh, it's this. It's more like a process, working from the outside in. Thinking about the region you're integrating over, thinking about each of the variables in turn, and the decision you make for some of the variables might dictate the values that you use for the other variables as well. Okay. So that's what our integral is looking like now. So now we can start to do it, so to speak. Well, here's something. The absolute value of sine phi, see, that's at the moment that's in this integral with respect to r and theta, but there's no r and theta there. So sine phi is just a constant in terms of r and theta, so I can push that out past those two integrals. Can't push it beyond the outer integral, because that's the phi integral. And I can drop those absolute value signs, okay? Because on this range, 0 to pi, sine of phi is always positive, so I don't need to put absolute value signs around. Okay, so NB sine phi is greater than or equal to 0 on the interval 0 to pi. I've got these other two integrals there, 0 to 2 pi, 0 to a, dr, d theta, and lastly d phi. Now there I'm just integrating the constant dr d theta. I've just got constant limits there. So it's just going to be the area of that rectangle, so to speak. So it's just going to be 2 pi a that I get from those two integrals. And that 2 pi a being the constant, I can shoot it out to the front. And 2 pi a k, it just reduces now finally to this. Suddenly now it's looking very, very doable. Sine of phi integrates to minus cosine of phi, and you're evaluating that at pi and 0. And what's that? That's minus the cosine of pi minus the cosine of 0, otherwise known as, Jack, you're up again. Otherwise known as? Let's hear it. 1, no. Try again.
0,
No.
1, 5.
Yeah, but what goes here underneath the whole thing? Come on, Jack, redeem yourself. Still got a chance? Two, you were just beaten to Anna, was that you? 2? 2, yes. You did say 2, but you didn't shout it out. Okay, good. 2. Four pi a k. Okay. So you see the benefit of, having gone to the trouble. I mean, the calculation of the Jacobian, that's only a one-time thing. We don't have to recalculate the Jacobian each time. That's just a fact now. The Jacobian of the transformation from Cartesian to spherical is minus r squared sine phi. So that's just something we can use now.
all the time. So once you go to the trouble of translating the integral into the new coordinate system, the actual integrals you have to go through are a lot more doable, a lot nicer than integrating square roots of sums of squares of x's and y's and z's. It's a lot trickier. And really, the way you integrate square roots of sums of squares of x, y, z's in reciprocal positions is using trigonometric substitutions, which is essentially what we've just done there by the transformation to polar coordinates. Are you about to point out another? Sorry, have I gone wrong?
Yeah, minus cos of pi minus cos of 0 is 0. So it should be like the swap the other way around, maybe.
So yeah, I've missed out a minus. It's minus minus. So sorry, what's oh my god. It's still 2, isn't it?
That makes it 2, yeah.
That makes it 2. Yeah. So that minus sign is that minus sign, and that minus sign is because you're subtracting the evaluations. Yeah. So it's still 2. 2 is still right. It's just my minus sign. Yeah. Okay. Okay, so that's good. So we've seen a number of examples of these transforming integrals into other coordinate systems. Okay, it's a bit of a blabber, but it does pay dividends in the end. Okay, so I think we'll leave it there. If you got individual questions or queries, feel free to come up.